Hi guys, welcome to Science in 5. In this video we're going to discuss Coulomb's law. Before you jump onto Coulomb's law, please make sure you understand Newton's laws of motion, you understand vectors in 2 dimensions, and your algebra is intact, because we're going to be using all those pre-learned ideas, all those background skills to explain Coulomb's law. Now, in words, Coulomb's law says 2-point charges in free space or air exert forces on each other, right? The magnitude of the force is directly proportional to the product of the charges and inversely proportional to the square of the distance between the center of the charges. According to Newton's third law, we know that the force is going to be equal. They're going to exert equal forces on each other based on Newton's third law. The first part on Coulomb's law that we need to focus on is the fact that the force is directly proportional to the product of the charges. Okay, so let's investigate that. So, F is directly proportional to Q1 times Q2. If I was to draw a graph of force versus the product Q1, Q2, I should get a straight line like that, which denotes a direct relationship. So, if only Q1 is doubled, what does doubling mean? Doubling means multiplying by 2. It means the force becomes 2F. Okay? If only Q2 is halved, what does that mean? Well, halving means multiplying by half. So the force must become a half F. If both Q1 and Q2 are doubled, a double, it means essentially we are multiplying by 2 and then we multiply by 2 again, which means the force becomes 4F. Okay, so that is about the first part where we say the force is directly proportional to the product of the charges. The second part of Coulomb's law mentions the idea that the force is inversely proportional to the square of the distance between the center of the charges. So, force is inversely proportional to distance squared. Now, if I was to plot a graph like this, the shape of the graph is no longer a straight line. Since it's an inverse relationship, I'm going to get a graph that looks something like that, right? Okay, and this relationship is referred to as the inverse square law. Now, how does an inverse square law work? Well, first identify the factor that is involved. You're going to invert that factor. That's the inverse part. And then you're going to square that factor. So if one quantity changes by a certain factor, how does the other one change? Well, it's going to change by the inverse squared of that same factor. Okay. All right. Suppose the force between 2 charges is 40 when the distance between the 2 charges is 1. If the distance between the charges is doubled, what will happen to the force? We know that the force is going to decrease because this is an inverse relationship. One quantity increases, the other one decreases. So, let's identify the factor here. The factor is doubling of distance. Doubling means times 2, right? With which we can actually write the 2 as 2 over 1. The next step that we need to do after identifying the factor is to invert that factor. So it becomes a half. So the inverse of 2 is a half. Then once we get the half, we need to square it. It becomes a quarter. So in other words, the force is going to decrease by a quarter. Or you're going to multiply the original force by a quarter to get the new force. So if the force was 40 newtons, 40 times a quarter gives us 10 newtons. So which means the force between the 2 bodies will now become 10 newtons. Okay, so increasing the distance between the 2 charges decreases the force. Identify the factor that is involved, inverse it and square it. We get by how much the force actually decreases. We can now actually get what the new force will be. Alright, we can also plot a graph of force versus 1 over r squared. Now, in the previous graph that we had, we could clearly see the coordinate points. When the force was 10, the distance was 2. So now if we're going to plot 1 over r squared on the x-axis, we're going to get 1 over 2 and then we square it. That gives us the 0.25. 1 over 1 squared will give us the 1. Okay, so now when we plot this graph, we're going to get a graph that looks like this, right? When the distance is 0.25, the force is going to be 10. When the distance becomes 1, the force is now 40. And we get a straight line like that. Okay. Now, just it's important to know these two types of graphs in case you might get these types of graphs and you need to identify them or work with them. Just know how these graphs operate. The moment you plot a graph of force versus 1 over r squared, it becomes a straight line. Force versus distance, you get this nice curve like that. Okay. Now, we've finished discussing the nitty-gritties of how there are two parts to Coulomb's law. Force is directly proportional to product of charges. Force is inversely proportional to the distance to the squared distance between the center of the charges. Now, in terms of a formula, Coulomb's law, the formula for Coulomb's law says F equals K Q1 Q2 over R squared. This formula is a summation of those two ideas that we've been speaking about. The fact that there is a direct relationship between the product and there's an inverse relationship between the squared distance. Okay. So now in the next part, we're going to just look at a calculation, a question. It will be good if you can try to work this question on your own and then see how your answers compare with what we got here. Okay. All right, let's go. The force between two charges Q1 and Q2 is F when the distance between their centers is R. All right, so the force is F like that. Right? What would be the new force in terms of F in the following scenarios? So 1.1, we're told that only Q1 is doubled. So we've mentioned that if you double one of the charges, so doubling means times 2. Therefore, the new force must be 2F. Because we have doubled one of the charges, so the new force must be 2F. That's the short way of doing it. The long way is to actually substitute into that formula what the new charge is and then see what the new force is going to be. So I would say the new force, F new, is going to be K times Q1 is now trebled. I said doubled. Okay, so I have to go back there. For 1.1, I said it's times 2 and the new force becomes times 3. It's actually times 3, guys. So it's times 3. Therefore, the new force is going to be 3F because treble means times 3. All right, got that out of the way. So it's going to be K times 3K1 times Q2. 3Q1 times Q2 all over R squared. The factor 3, we can take it out. We can now end up with 3 times K Q1 Q2 over R squared. But we know that the K Q1 Q2 over R squared is the same as F. So this becomes 3 of F. So this is the long way of actually doing it. But you can actually do this almost like a logic way to say, oh, yeah, since there's a direct relationship, you times 3 this side, you times 3 that side. That can also work. Okay, so 1.1, the answer is 3F. Okay. All right, let's move on to 1.2. Now 1.2 says, well, both Q1 and Q2 are quadrupled. So 1.2 quadruple. When you quadruple Q1, you multiply by the force becomes 4 times larger. Quadruple Q2, the force becomes 4 times larger as well. So the total effect is 16. So the new force must be 16F. And again, we can prove it by doing the long algebra process, where we say new force is going to be K times 4 Q1 times 4 of Q2 all over R squared. The 4 times 4 becomes 16, so this is 16 times K Q1 Q2 over R squared. And we know that K Q1 Q2 over R squared is the same as F, so this will give us the force as 16F. So here the answer is 16F. Okay. All right. Now 1.3, the distance is quartered. In other words, the charges are brought closer to each other. The distance is 4 times less than what it was initially. So we are talking about the distance becoming smaller. So the force must get larger. How does the force get larger? Well, remember we said force and distance have got this inverse square law. We use the inverse square law. So basically identify the factor involved. It's a quarter. What we're going to do to the quarter, we're going to invert. It becomes 4. And then we're going to square. Becomes 16. So the new force is 16 times larger. Again, we can prove this. So 1.3, the answer is also going to be 16F. Again, we can prove this by using an algebraic method, which is a little bit longer, but we can actually again prove that the force is going to be indeed 16F. So let's do that. So the new force will be, the charges are the same, so it's K Q1 times Q2 all over. The distance is now a quarter of the original, so it's a quarter of R, and all of that is squared. Right? We now have K Q1 Q2 all over R squared over 16. Now we can simplify this easily. Remember one of the ideas of dividing fractions. So this is K Q1 Q2 divided by R squared over 16. This line here means division. So we can change division to multiplication, then we invert 16 over R squared. So this becomes 16 times K Q1 Q2 over R squared. This is same as 16 of F. Okay, so you can actually do the long method, the algebra method. I think for practice, I also encourage you to do the long algebra method and see if you get the same answer. So the answer is 16F for 1.3. Now, 1.4, we are told that Q1 is doubled, Q2 is trebled, and R is also trebled. Okay, how can we figure this out? I normally start with the hard one. The hard one is the little bit harder one is the distance. Remember, the force and the distance have got the inverse square law relationship. So for R, the factor is 3. Trebling means 3. You invert 3, it becomes 1 over 3. You square 1 over 3, you get 1 over 9. So the new force is going to be 1 over 9 times. So the effect of trebling the distance makes the force 9 times smaller. Q1 is doubled. That means times 2. Q2 is trebled. That means times 3. So now the new force is going to be 9 times 2 times 3 of F. So this will give me 6 over 9 of F, which is the same as 2 over 3 of F. Again, you can do an algebraic process. Can you do an algebraic process to prove that the force indeed becomes 2 over 3F? Yes, you can do an algebraic process. It's going to be a little bit longer, but let's see if we can do that. So we are saying the force here becomes 2 over 3F. Let's prove that again by going through a little bit lengthy algebraic process. Let's go through this lengthy algebraic process. Good for the practice for maths, good for science. Okay, so we are saying the new force is going to be Q1 is doubled, so it's now K times 2 of Q1 times Q2 is trebled, which is now 3 of Q2, all over R is trebled, the distance is now 3R squared. Right, this will give you 2 times 3 is 6, so we're going to have 6 of K Q1 Q2 all over 3 squared is 9. This is 9R squared. We can take out the 6 over 9 there. We're going to end up with 6 over 9 times K Q1 Q2 over R squared. 6 over 9, we've just shown that it's 2 over 3 times K Q1 Q2 over R squared is the same as F, 3 over 2 of F. Okay, right, let's move on to the last question. 1.5. F equals K Q1 Q2 over R squared is our general formula. Now we're told Q1 is doubled, so the new force is going to be 2 times Q2 is quadrupled. Quadrupled means times 4, and the distance is halved. So we know that the distance is halved. We can work this one mentally. Inverse of half is 2. 2 squared is 4. So the force becomes 2 times 4 is 8 times 4 is going to be 32 of F. Can you do an algebraic process to show that the force will be 32F? You can do that for practice. Okay, so that's it about Coulomb's law, guys. The force has got 2 parts. The first part is directly proportional to the product of the charges. Second part, inversely proportional to the squared distance between the centers of the charges. In our next video, we're going to look at how to perform calculations involving Coulomb's law. Thanks for watching, guys. I'll see you guys around next time. Ciao.